slow down, your velocity changes in time. This is called acceleration. The average acceleration is defined as the change in velocity divided by the time interval. Notice that acceleration is a vector quantity with units of length divided by time squared. In the limit that the time interval goes to 0, the instantaneous acceleration is the derivative of velocity with time. Since velocity is the derivative of position with time, acceleration is also equal to the second derivative of position with time. Graphically, acceleration is the slope of a velocity-time curve. For the case when the plot of the velocity with time is a straight line, is the acceleration 0, constant, or variable? Correct. Since the slope does not change, the acceleration is constant in this case. When motion is along one dimension and the acceleration is constant, a set of equations can be derived that defines the motion completely. The velocity is the initial velocity plus the acceleration multiplied by the time. The position is the initial position plus the initial velocity multiplied by the time, plus 1/2 the acceleration multiplied by the time squared. The third equation is derived from the first two, eliminating time as a variable, and relates velocity, acceleration, and position. To derive the velocity equation, recall that acceleration is the time derivative of velocity. Moving dt to the other side with a, integrate both sides. For constant acceleration, a moves in front of the integral. After integration, we can then solve for velocity. Velocity is the time derivative of position. Moving dt to the other side, integrate both sides to get the position. Note that the integration of the last term on the right gives you the 1/2 and time squared. Let's go through an example together. A car is traveling east and uniformly reduces its speed from 45 kilometers per hour to 30 kilometers per hour over a distance of 250 meters. What is the car's acceleration and what is the elapsed time? A good way to start on any problem is to draw a picture to visualize what is happening and then write down the information given in the problem, such as the initial and final velocity and the distance traveled. We are trying to find the acceleration. Which parameters are known? Correct. Now that you determined the known parameters, choose the correct equation that can be used to find the acceleration. Correct. You are trying to find acceleration, so now use the equation to solve for a. Once you have an expression for acceleration, you can plug in the numbers. But everything should be in MKS units. Which of the given parameters are not in MKS units? Try again. Correct. The velocity should be in meters per second, but are in kilometers per hour. Use the conversion of 1,000 meters equals 1 kilometer, and 1 hour equals 3,600 seconds for both the velocity and initial velocity. Then, put these in the equation for acceleration. The answer is a negative number. What is the significance of the negative sign? Correct. Since acceleration is a vector, it points in the direction opposite the motion and thus is slowing down. Now that you have the acceleration, you can go on to the next part of the problem, which is to determine the elapsed time. Which equation should you use? Try again. Correct. Solve for the time and then put in the numbers. Notice that time should always be a positive number. An example of one-dimensional motion is free fall when an object accelerates due to gravity. You can use the same equations we have already found for one-dimensional kinematics, but using some standard conventions often used when dealing with free fall. On the surface of the Earth, the acceleration due to gravity is a fixed constant given by the symbol g. G is always positive and is equal to 9.81 meters per second squared. Usually, since an object moving up or down travels in the vertical direction, the coordinate axis is taken to be in the positive y direction away from the Earth perpendicular to the surface. Thus, the acceleration of an object in free fall is minus g, which indicates the object is accelerating towards the Earth. Thus, we can rewrite the equations of motion for an object according to this convention. Let's do a simple age-old experiment that involves free fall. Aristotle claimed that the speed of a falling object depends on its mass, or, in other words, heavier objects fall faster. Galileo, on the other hand, said the contrary, which is that the speed of a falling object does not depend on its mass. Who do you think is correct? Let's find out by dropping two objects of different mass from the same height. According to Aristotle, the heavier object should hit the ground first. Galileo would say that the two objects should hit at the same time. Galileo was correct. The speed of a falling object is independent of mass. Before we move on, here is something to think about. Although we know that in free fall an object's speed is independent of mass, why does a falling feather not seem to obey this rule? For our simple experiment, let's say we didn't know the value of g, the acceleration due to gravity. If we measure the height of an object before it is dropped and the time it takes to fall, we should be able to calculate g. Which equation do you use? Correct. Now choose a coordinate axis with y positive away from the Earth and the surface of the Earth at y equal to 0. Thus, y0 is the height. But what is the initial velocity v0? Correct. The object is initially at rest the instant it is released. Now you can solve for g. Then put in the values for y0 and t. Lo and behold, we are on the Earth. So if you ever find yourself on an unknown planet, you can determine its gravity if you have a stopwatch and a measuring tape. Speaking of falling objects, remember the falling feather that seemed to defy Galileo? Two words sum up the answer: air friction. Strictly speaking, Galileo is only correct in a vacuum. This was verified when NASA put a man on the moon and dropped a feather in a vacuum.
How about that?
Ball 1 is dropped from a height of h1 meters. At the same time, ball 2 is thrown downward from a different height of h2 meters, which is also unknown. Use the simulation and analytical calculations to determine the value of h2. One way to solve this problem is to use the simulation and input a value for v0 such that the two balls hit the ground at the same time. When this condition is met, Use the V0 and time t to solve this problem for H2. Input a value for V0 and click on the Run Simulation button. The two balls did not land at the same time. Please try again.